Okay, for this video, I'll be going through turning effects of forces, which is basically moments tutorial. Okay, so all these are the success criteria. Okay, so the first question, in figure 1, a uniform meter rule. So I would like to underline this, and if it's uniform, that means the CG is in the center. Okay, and this is a meter rule, so it is 100 cm in length. That means the CG is at the 50 cm mark. CG at 50 cm mark. Okay, and it is pivoted at its center. That means supported at its center. That means the pivot is over here. So the pivot there is actually at the CG. All right, and it is now balanced. So if it's balanced, that means later on I can apply principle of moment. Right, A and B each weighing 50 Newton. Okay, and 40 Newton respectively. So I draw the forces here. For A, it is 50 Newton. For B, it is 40 Newton. Okay, so these are the two forces acting on the rod. However, there are actually two more forces. Okay, there are two more forces acting on rod other than the weight of the 50 Newton and the 40 Newton. Okay, so actually one of it is the weight of the rod. Okay, so this force acted upon by gravitational pull of Earth. Okay, and there is also a normal force, right, that's acting on the rod. Take note, these two, although they are equal in magnitude and opposite direction, they are not a pair of, not Newton's third law, pair of action and reaction forces. Okay, and the reason why we are not later going to use these forces in our calculation in moments is because, very important, okay, these two forces passes through pivot, right, or is acting at the pivot point. So if it passes through the pivot, the perpendicular distance is 0, right? That means moment due to these forces, which is force times perpendicular distance. Since your perpendicular distance is 0, therefore your moment should be 0. So we actually do not need to bring in these two in our calculation. Okay, so when we solve moment calculation question, we go by these 6 steps. Okay, let me pause the video. Okay, so these are the 6 steps that you can apply when you are doing moments question. So firstly, identify where the pivot is. So as stated in the question, this is step 1. So it's actually at the 50 cm mark. Okay. Next, number of forces there are acting on the rod is actually 2 forces. We have 50 Newton and also 40 Newton. Then just now I mentioned that there are 2 more forces, which is the weight of the rod due to gravitational pull, and also the reaction force due to the pivot supporting it. Okay, but because they are both passing through the pivot, we will not count them. Okay, so we actually have to just account for the perpendicular distance of these 2 forces. So this is my step 2. I have 2 forces here. Then for step 3 is the perpendicular distance of each force. So you need to draw your line of action of the force. Okay, so you just extend the forces using dotted line. Okay, front and back, and then because your pivot is over here, this will be the perpendicular distance for B. This will be the perpendicular distance for A. Okay, so take note that the perpendicular distance is usually the shortest distance. So I can actually write down my step 3. For A, the force is 50 Newton, the perpendicular distance is 20 cm. For force of B, which is 40 Newton, the perpendicular distance is actually D. So I take it that is cm, because then it will cancel out with the other side when we are doing the principle of moment. Okay, then you can calculate the moment for each force. Step 4 will be 40D. Step 4 for this side will be 1000 Newton cm. Okay, then step 5 is to account for the direction. So I would need you all to take a pen and hold the pen at where the pivot is, which is at the center. So you hold the pen at the center, and for the direction of moment due to A, you press down on the left hand side of your pen while still holding your pen at the center. So if A is acting downwards and on the left hand side, it will then create a anti-clockwise direction moment. Okay, then you repeat for the moment of this 40D. Same thing, you hold the pen in the center, right, because that's where the pivot is. You apply a force downwards, right, for B, and it must be applied on the right hand side of the pivot. You will then get a clockwise direction. Okay, so step 6, you apply your principle of moment, which is clockwise sum of anti-clockwise moment equals to sum of anti-clockwise moment. So I'll have 1000 Newton cm equals to 40D Newton cm. Okay, notice that the units actually tallies and they can be cancelled out. Okay, they can be cancelled. So not really cancelled. It's just that both sides were using cm. Then that's okay. So after that, I calculate for my d. The d will be 25 cm as stated here. Okay, so some of you may be able to do this without applying the 6 steps, because this is like a very common sense kind of question, right? But still, I would like you all to learn about these 6 steps. Okay, question 2, it is a more complicated kind of question. So let's again go through the 6 step. Let's read. It shows an electrically operated barrier arm. The arm is pivoted at P. Alright, so this is our first step. The pivot is over here. We can use a triangle to represent it. And the weight is counterbalanced. If it's counterbalanced, that means it is now in equilibrium. So later on, step 6, I can apply my principle of moment. Okay, so it's counterbalanced by the weight of M. So M is acting over here. And M's actually has a weight, which is W. Okay, acting downwards and on the left hand side of the pivot. Now the arm weighs 250 Newton and the center of gravity is 2.4 meters. So they tell us where the 250 Newton is acting on with respect to the entire arm. And the center of gravity of M is 0.4. So by this, they already tell us the perpendicular distance. Okay, but I'm going to run through the 6 steps again. Step 1 is pivot is at over here. Okay, this point here. So I have actually 2 forces, the 250 Newton and M. Okay, or weight of M. So I have 2 forces. Now, step 3 is to determine the perpendicular distance. So over here, step 3, it will be 2.40 meters. For here, it is W, and my step 3 perpendicular distance to the pivot is 0.40. Step 4 is to calculate your moment. So equals to 250 times 2.40. Okay, for the weight, it is 0.40 W. Okay, at the same time, I noticed that they have the same units for their length. So I don't need to worry later, because they will be sort of cancel out eventually. Now step 5 is to find the direction. So again, we hold a pen, okay, with the pivot slightly to the left hand side of the pen. Okay, don't have to be too exact. And for this 250 Newton, it is on the right hand side of the pivot and is going downwards. So it will give a clockwise direction. Okay, so for this 0.40 W moment, the force is acting on the left hand side of the pivot. So if you hold the pen slightly on the left hand side, but you still apply a force W downwards on the left hand side of the pivot, you will get an anti-clockwise direction. And the question already tell us that it is in equilibrium, counterbalance. Okay, so it means balance. That means I can apply my principle of moment. So I will have 0.40 W equals to 250 times 2.40. Okay, so I should get 1500 Newton. Okay, so this is still easy. Let's keep on applying the 6 steps. Okay, in figure 3, a driver's footsteps on a car's brake pedal applying a force. So we see that there's one force here. As a result, the tension in the spring is 160 Newton. So I have another force that is applied on the string, and because the spring will be pulling back, right? Will be pulling back. So the force is actually 160 Newton. Okay, so step 1, pivot is here. Okay. Step 2, I have two forces, 160 Newton and F. Okay, they did not give us anything about the weight of the this brake pedal, so we don't need to care about it, right? Okay. Step 3, the perpendicular distance. Okay, so for the F is pretty straightforward. You draw your line of action of the force of F, okay, and pivot since it's here. The perpendicular distance is 40 cm. So step 3, it is 40 cm. Okay. Take note for the 160 Newton, not so straightforward. Again, you draw line of action of the force, okay, and again pivot is here, right? So the perpendicular distance will then be 5 cm. Okay, so this is the step 3. Perpendicular distance is 5 cm, and again I make sure that the units of the distance are the same. Step 4 will be calculating the moment, so equals to 5 times 160 Newton. Okay, 5 cm multiplied by 160. For this will be 40 F. Okay, now we need to apply the direction. So for F, the moment due to F, it will be anti-clockwise. Okay, the moment due to the 160 Newton. Okay, so in this case, you can actually hold the pen this way. Okay, you hold a pen this way, and pivot is here. You hold it here. You apply a force of 160 Newton on top of it. So you try to use your pen to look like this scenario, and it will then give me a clockwise direction. So step 5 is clockwise. Okay, so step 6. Okay, we apply principle of moment. So will be 40 F equals to 800. So therefore, my F will be 20 Newton. Okay. Okay, in figure 4, tension T is exerted by the hamstring at the thigh to hold the lower leg at a vertical position, while a weight of 50 Newton is tied to the ankle. Okay, so they want us to calculate the tension T. Okay, that is due to the hamstring muscles. Okay, so step 1, pivot is here. Okay, this is my pivot. Step 2, how many forces are there? T and this 50 Newton. But this 50 Newton, it will be extended this way. Okay, so because this 50 Newton will be going down, being pulled down by gravitational attraction, therefore, when it extends back to this string that is tied over here, it is in this direction. Okay. Step 3, which is the difficult part, finding the perpendicular distance, but we have this 4 cm, and you see, if I were to extend the force, drawing the line of action of the force, we see that the pivot is here, then this will be the perpendicular distance. So we have 4 cm, okay, and T. For this 50 Newton, the perpendicular distance is actually 42 minus 4. Am I right? No, it is just 42. Okay. So let me draw my line of action of this force. Okay, so we see that it goes down all the way to where the pivot is. Yes. Okay, so it's actually 42 cm. Okay, then step 4, we calculate the moment, which is T multiplied by 4. For the 50 Newton will be, the moments will be 50 multiplied by 42. And again, we make sure that the units correspond to each other. Okay, step 5, let us find the direction. So this one will be clockwise. For this will be anti-clockwise. Okay, for the 50 by 42. Then let's assign sum of clockwise equals to sum of anti-clockwise. So 50 times 42 equals to 40. Therefore, your answer should be 525. Okay. So if you follow the 6 steps systematically, it is quite simple. Okay, calculate the weight of block B. So now there are actually a few forces, more than two. So far we have been doing two forces, okay, but now we have three forces. So step two, pivot over here, step one, then we have one more force here, step two. Okay, perpendicular distance for the 3000 will actually be 10 meters. For the weight is actually step 3, 2 meters. For this B, weight of B is actually 4 meters. Then we calculate the moment, we assign the direction. Okay, you should be getting 8,000 Newton. So please try this. So sometimes things can become more complicated, because if I were to identify any forces perpendicular distance to be incorrect, then the whole thing will be wrong. Okay, so make sure you draw your line of action of the forces to help you. Okay, draw your line of action of the forces to help you. And most important thing is identify where the pivot is. So now they say they change it, calculate the distance of block B from the pivot if the load is reduced to 2000. So if over here the load from 3000 it changes to 2000, then I will have a lower total clockwise moment, right? I will have a lower total clockwise moment. So if B doesn't change its distance to the pivot, then the anti-clockwise moment will be greater than the lower total clockwise moment. Therefore, this B must shift. Okay, so this is to keep the crane balance. Okay, so then you can do your calculation again. Something has changed, the force has changed, the weight has changed, but the weight of the jib of the crane remains at 1000 Newton and is still at 2 meters away. That one can't be changed. Okay, then you can do, and then you'll find that the distance is actually 2.75. Right? Please try it out using the 6 steps. Now question 6 shows a hanging ornament with 2 birds and 2 bees. The weight of the bee on the lower left is 0.4. So I take note of that. Okay. Assuming the hanging bars and the strings have negligible weight, okay, determine the weight of the bee on the lower right. So this is the bee on the lower right, and for this part of the system, the pivot is over here. Okay, so again, you apply the 6 steps, you should be able to get the weight of the bee to be 0.800 Newton. Okay, now they want us to determine the weight of the bird on the middle right, the weight of the bird. So actually, now there is a total combined force of this B and this B weight, right? So it's 0.4 plus 0.8. So I have 1.2 Newton here. And we repeat the process. We take note that now the new pivot is over here for this part of the system. Okay? So you should get the weight of this bird to be 2 Newton. Okay? So it's as if, to make it clearer, it's as if I were to remove this whole thing, I should replace it with a force of 1.2 Newton, because that is the total downward force exerted by this 0.4 and this 0.8. Okay, so I can actually erase this. I don't want this. I can actually replace it with a 1.2 Newton. Okay, and that will help me to solve for the weight of this bird on the right. Then the weight of the bird on the upper left. So if I look at the answer, the weight of this bird is 2 Newton. Okay, the weight of this bird is 2 Newton. Here is 1.2. This is 2 Newton. So total, the weight that is pulling down is, on this side, is 3.2 Newton. Okay, so after that, you choose your pivot to be here again, and then you can find the weight of the last bird. Okay, so slowly work your way up. Okay, question 7. A curved object is resting on a support M with the center of gravity C below it. So in figure 7.2, one end of the object is lifted by an applied force. As a result, the object is tilted but remains stationary, which means that it is in equilibrium. Okay, so on figure 7.1, draw and label 2 arrows that represents the weight of the object and the normal force acting on the object. Okay, so because the center of gravity is here, right, it's not over here, or not over here, not over here. Okay, it is labeled as center of gravity here. So you must draw your weight directly from the center of gravity. But why doesn't this rod falls to the ground? Because it's being supported by a normal force. And because both forces are passing through the pivot, if you were to draw the line of action of the force, they will pass through the pivot, which is here. Therefore, there will be no turning effect. So this is how you balance things, isn't it? Now, in figure 7.2, the object is balanced by force F and 3 other forces. Okay, because now it's tilted, right? So draw and label these 3 arrows. So first one is W, is still acting vertically downwards. But normal, it must be acting 90 degrees to the surface. Okay, 90 degrees to the surface. So it is drawn like this. Okay, 90 degrees. And by right, this thing would have slipped off, isn't it? Okay, so what do I mean by that? Yeah, it should have slipped off. It would have fallen off, but because there is now this friction force. Okay, there's now a frictional force. Yes, okay. So explain the subsequent motion of the object in figure 7.2 if force F is removed. As the object was in rotational equilibrium before force F was removed, right? It says that in figure 7.2 it remains stationary. Okay, and why does it remain stationary? By right, this W should exert a what you call that? Clockwise moment, right? There's this perpendicular distance. Okay, so by right it should swing clockwise, but it didn't, right? Because this force is actually exerting a anti-clockwise moment. It's exerting an anti-clockwise moment, right? So this force F is actually exerting an anti-clockwise moment. Sorry, let me draw the line of action of the force. Okay, so this is the pivot. That means if I apply an upward force on the right hand side, it will create an anti-clockwise. So these two actually balance off each other. Whereas the friction and the normal force being passed through the pivot will have no moments. Okay. So as the object was in rotational equilibrium, which just means that no net moment. Okay, there was no net moment. Right, but since the moment due to force F is anti-clockwise, yes, the removal of force F will result in a net clockwise moment. So if I were to remove F and its anti-clockwise moment, there will only be a clockwise moment. So now there's a net clockwise moment of the object, and therefore the object will rotate clockwise until it is in a position of stable equilibrium, whereby the center of gravity C is directly below the support M. So it will then go back to become 7.1, whereby the forces will pass through the pivot. Therefore, there will be no perpendicular distance and no moment, right? So this is how things that they actually they sort of swivel back and forth until they become stable. Okay, question 8. Figure 8.1 shows the cross-section of an egg-shaped toy that consists of a thin plastic shell, which I know is low density. Okay, and then they have some lead at the bottom, which is high density. Okay, when the toy is knocked over, as shown, it will always roll over. So this is what they tell us. This is a kind of toy. And return back to the upright position. They want us to label. Use the cross to mark the center of gravity for the plastic shell and label the cross as P. So done it here. Okay, because this whole thing is made of plastic shell, so I choose the geometric center. Geometric center for this egg shape. Okay, but because the lead is over here and we have more lead on top, so it should be slightly higher. Okay, and take note that it must be above this pivoting point, right? That's why when you set it up like that upright, it does not swing left and right. Okay. On figure 8.2, mark and label all external forces acting on the toy. So because the lead actually has a higher density, so it seems that all the weight for this whole entire system is nearer to the lead. Okay, so because I added the lead, the center of gravity actually drops to a lower position. So there is a normal force where you can somewhat take it as like the pivot, and you also have the weight of the entire system, which is the plastic shell and lead, somewhere here. Okay, so explain why the toy is always able to return to its upright position. As you can see from this diagram, there are actually two forces. One is the normal force being supported by the table and in vertical position, and because the pivot is right over here, there is no perpendicular distance. Therefore, the W is the one that has the perpendicular distance, and therefore it will have a clockwise moment. So if it's clockwise, doesn't mean that this egg-shaped toy will swing in a clockwise direction. Okay, so now that you understand this, let's put it into words. The toy is in stable equilibrium. What is stable equilibrium? That means the CG is raised, and when it's unstable, the CG will return to a more stable position. I'll see if I have time to explain this later. When displaced in figure 8.2, the center of gravity of the toy is raised. Is it true? Yeah. You see, actually this is where the CG of this whole toy is. Take note, is the whole toy. So it's somewhere here. Okay, something like this. So at this position, okay, the CG obviously is lower than the position of this CG in 8.2 because it has been displaced. It has been displaced, right? Therefore, when I displace it, the CG goes higher. Okay, and when the CG goes higher, right, the CG is raised, mentioned over here. Therefore, it will result in a stable equilibrium. Okay, so for stable equilibrium, it means that the CG is raised, okay, when it's unstable, and therefore it will return by lowering the CG. But if I were to explain using moments, okay, the weight of the toy results in a net clockwise moment. Okay, so you can actually sort of memorize this as a template, but you must apply it to the question. Okay, so it will result in a net clockwise moment, and this causes the toy to rotate clockwise back to its resting position and lowering its center of gravity back to the equilibrium position. Now, it doesn't mean that the toy, when it rotates, right, clockwise, okay, it doesn't mean that it will, because it's rotating clockwise, right, it doesn't mean that it will cause it to stand upright straight away. It will still continue, right? But the amount of clockwise and anti-clockwise motion will get lesser as time goes by. So eventually, it will end up looking like that with the center of gravity above where it is being supported. Okay. Okay, then question 9, again, same thing. It's a children's cup that always returns to an upright position. So if they tell us that it always returns, right, that means the CG is raised when it's unstable, okay, and will be lowered to become stable. Okay. So what is meant by center of gravity? It is of the cup. It refers to the point through which the whole weight of the cup appears to act. So this is a definition that you need to know. On diagram A in figure 9, assume that the handle has negligible mass. Mark out the center of gravity. So it will be somewhere here because the question already tells us that it always returns. That means the CG, it is located at the bottom. That's how it can return. And describe and explain how the car is manufactured such that the center of gravity is at this position. It's made of a denser or thicker or heavier material than the rest of the cup, right? So it results in a lower center of gravity. Now, in order for something to be stable, there are two factors. The first one is the lower the CG, the more stable, okay? And the larger base area. Okay, so explain how the cup is able to return to its upright position when it's tilted to position B. So the CG will still be here. Do you notice that the CG when it's unstable is higher than when it is stable? So C shows that it's stable. A shows that it is unstable, right? Because after that, it will rotate clockwise. So you see that the CG position is higher than the CG position in C. But the position within the cup for the position of the CG within the cup is still the same, right? Unless something drastically changes the internal makeup of the cup. Okay, so what I'm saying is that the height of this CG above ground for A is definitely higher than the height of the CG above ground for C, right? So the cup is in stable equilibrium. When displaced, the center of gravity is raised, right? So the weight of the cup results in a net clockwise moment about its center of contact with the surface below. So try to use the context to say whether is it clockwise or anti-clockwise. So, and this causes the cup to rotate clockwise back to its resting position and lowers its center of gravity back to equilibrium position. Okay, again, you can sort of use this as a template to answer to explain your CG or moments question or stability question, but you need to apply it to the context. Let's do one more. Question 10. Okay, so this is a toy bird at rest. The center of gravity is marked as G. Okay, so it is within here. So that is the purpose on why they want it like that, because they can make it to be stable. So 10.2 shows the toy bird at a displaced position. Now, if the center of gravity is this way, in between the beak and this part of the tail, when I tilt the bird in this way, it must still be at the same position within the object. Okay, within the object. Okay, but you notice that the height of the CG is actually raised. Okay, the height of CG above a reference point or reference level, the height of CG is raised. Okay, and we know that when it's raised, it will be lowered to stable. Okay, the height of CG is raised when unstable. We know that this toy is going to flip back. Okay, so explain why the toy bird eventually returns to its resting position when it's displaced and released. The toy bird is in stable equilibrium. Okay, because they tell us that it will return to its resting position when displaced and released. So when displaced, the center of gravity of the toy bird is raised, right, as I've shown up there. The weight of the toy bird will result in a net clockwise moment. This one based on the context. Use the pen trick to help you determine whether is it clockwise or anti-clockwise. And this causes the bird to rotate clockwise and lowers the center of gravity back to equilibrium position. Okay, question 11. In figure 11, a boy lying in a reclining seat discovered that he can rock himself back and forth by swinging his arms as shown. Using concepts about moments, so when they tell you to use concepts about moments and CG, you need to include in your answer. Okay. Okay, so explain the phenomenon. So when he is in the equilibrium position, his pivot is here, right? This is the only supporting point. So the CG of the boy is actually much higher. Okay, so as he swings his arm backwards, when he swings his arm backwards, the CG is shifted. Okay, so maybe to here. So now there is actually a perpendicular distance between the line of action of his weight and the pivot. So this is the perpendicular distance. So he will then swing clockwise. But if he wants to swing backwards, okay, he wants the thing to rotate in the anti-clockwise direction, he will then swing his hands down so as to shift the CG. Okay, so for this boy, because he is a living thing, okay, he can shape his hands and legs, he can put them in various positions, the CG will change. But for the cup, because it is not a living thing, for this cup, it is not a living thing, so it's unable to change the way how he places his different parts of the cup. But for the boy, the CG will change. Okay, so again, as the boy swings his arm, his center of gravity is shifted. This causes the line of action of his weight to be shifted away from the pivot. What does this mean? It means that there is a net moment about the pivot because there's a perpendicular distance, right? As shown from here. So as a result, his weight produces a net moment about the pivot, which is clockwise. If he swings his arm towards his head, right? If he raises his hands, and anti-clockwise if he swings his arms towards his feet. So hence his body will be able to rotate clockwise or anti-clockwise due to the swinging of his arms. Okay, so I will say that for moments, right, the calculation is more simple. Once you follow the 6 steps, it's easier. Okay, if you have time, you need to look at the 2 pivot question. Okay, there are 2 pivots question, right? Because example, if I have a rod is supported by 2 points, 2 lines, then there will be, this becomes a 2 pivot question. So the way to solve this kind of question is by choosing one of the point of support to be the pivot, and this will be used as the reference point to calculate my perpendicular distance. Okay, so the calculation questions, if you apply the 6 steps, is very simple, but the explanation questions, you need to maybe do a few TYS and look through the answers to see how you can come up with your own answering templates, or you can use the ones that you see in your tutorial.